So to talk about continental drift, we have to talk about someone named Alfred Wagner. He was a polar researcher, and he was studying the polar environment at a time when going to the poles, were north and south, were heroic. They were the places where adventurers went. He was born in Germany in 1880, about the turn of the last century. He discovered, he didn't really discover, he came up with an idea that was interesting. As he was studying the poles, he looked at how glaciers moved, and it was a struggle to get there. It was a struggle to see how the world changed, how the glaciers could how the glaciers moved and floated, how they crushed each other, what happened when they collided, what happened when they separated. Now this is very telling because one of the things he discovered was continental drift. Again, I hate to use the word discover. He thought of an explanation, a theory that would explain all the observations he had made up to that time. This story is better told by the video that I'm posting on the website, but I'm kind of summarizing it here. The bottom line is that Alfred, while talking to one of his roommates, looked at a map and he noticed that the southern tip of South Africa, or the eastern tip of South Africa, fits into Africa. South America fits into Africa. That all these pieces of the world fit together like a jigsaw puzzle. And being an educated man, he also knew it wasn't just this outline, but he knew that the various levels near the coast, underneath the oceans, also matched. Through his research and world travels, he knew that the fossils matched, that the fossils found here in South America matched the fossils found here in Africa. The fossils here in North America matched those found in Europe. He knew, for instance, that the Appalachian Mountains had the same rock strata, the same rock structures that are found in Scotland. He knew that India shared fossils with Africa. He knew Australia shared fossils with and rock strata with other parts of the continent, even though Australia is completely separated from any major continent. So he theorized that all these components of the continents at some point fit together. Now, at the time, he was not a geologist, so the geologists really didn't take him seriously. But the botanists took him seriously, and they said his theory explained so much. It explained why the biodiversity on the various continents, the fossil records matched, why he saw that they saw, and I'm going to put on the website an interactive world map that shows you every fossil found up to this point, and you can actually click on the fossil evidence and it'll tell you what the fossil is, and then you can go on the opposite side of the world and click on that evidence there, and you can see that the fossil evidences do match. In fact, the components, you can take a broader view, you can zoom out and see where all the fossils are on the planet in a region and look at their composition. You can see the composition of the rock strata, how old the rock strata is, and you can also then look at what different animals or plants you found in that rock strata and compare it to South America to Africa. It's a very interesting interactive map. Fun, I think. Now, the problem with Alfred Wagner's theory is that he didn't have an explanation of what could possibly move continents. Now, the Europeans at the time thought that the continents were either sinking or lifting. And they were thinking about that because of, I would hope, is because of the mountains, how they were trying to explain mountains. The North American scientists just felt that this was the way it is and the way it's always been, and the structure of the continents were not changing much at all. But Wagner said they were both wrong, that the continents were changing, they were moving, but they weren't moving up and down the way the Europeans thought, and they weren't static the way the North Americans thought. They were moving horizontally. The problem that he had is that he could not explain what mechanism could possibly move all the continents of the world. Not just a mountain, not just a valley, not just a city, but all the land of North America moving somewhere, and all the land in South America moving. The forces necessary to move such land masses, he just could not explain. And even though he had very strong fossil evidence, and you could look at the geologic record, and you can see the link, a lot of scientists felt there must be some other explanation. Well, he died in 1930 of a heart attack while he was in the North Pole on a trek to get more supplies for his base camp. Of course, World War I happened, World War II before he died, and then World War II after he died. Now, during World War II, we had a lot of ships in the Atlantic Ocean. Now, in the Atlantic Ocean, most scientists at the time thought that the bottom of the ocean was going to be flat. It was going to be all sandy and flat. Makes sense. Like a giant beach, if you will, but underwater. As North American troops and supplies were going to Europe for the war, the Germans had a lot of U-boats or submarines that were sinking our ships. So we sent out ships with magnetometers or Gaussian meters, and they would measure the magnetic fields in the ocean, hoping to find submarines before they could blow up our ships. This is before sonar, right? Before the end of World War II, they developed sonar, and they were able to find the ships. Well, one of the Navy captains, later after the war, continued to measure the magnetic fields on with a long cable with the magnetometer or Gaussian meter at the end. He'd sink it down, and he would travel back and forth across the Atlantic Ocean, trying to find the various magnetic fields, because what they found was that the magnetic fields changed as they took rock samples too from the bottom of the oceans. The interesting thing was that the orientation of the magnetic field along this, there was a center line. The center line ran from Iceland, which is above Greenland. I'm not sure which way it goes, but something like this, probably above Greenland, Iceland. And on each side they had of this line, they had a layer of rock whose magnetic field was oriented in one direction. So all the rock they sampled here all the magnetic fields were oriented, let's say, towards the north, the way a normal compass would be oriented, all right? And along the other side of that red line, the magnetic field was also oriented with the compass pointing north. That was expected. But then on the right next to it was a layer of rock where the compass, the magnetic field, would point south. So if you put a compass on it, the compass would point south instead of north. So the magnetic lines were reversed. And a little further down, a little further away from that, they were back to pointing north again. On both sides, again, on both sides of this red line, this midline. And this kept going all the way across the Atlantic Ocean. He's noticed and documented that these rocks at the bottom of the ocean, their magnetic orientation reversed, polarity, over and over again. One layer was pointing north, the next layer was pointing south, and it just kept doing that on all the way up to the continents. And he couldn't explain why, but certainly it was an odd description. At first no one could figure out what could make rocks point in the magnetic field of a rock point in the opposite direction of the opposite direction of all the rest of the rocks on the planet. The rest of the planet on the surface is on the continents, all the magnetic fields generally pointing north. It was strange. Unless you were over like a metal, iron deposit, might make your magnet swoop around. But on each side of this layer, Atlantic Ocean, across this mid-Atlantic line, the middle of the Atlantic line, there were these rocks. The polarity of the magnetic fields kept flipping on both sides. So it was just really strange. And after thinking about it, the only thing they could think that could possibly allow that to happen is if there was now remember, the Earth's magnetic field is such, and it's not quite as neat as I'm drawing it. It's actually neater than some planets. Some planets like Jupiter, their magnetic fields are wild, but ours does fluctuate, and this is a horrible drawing, but it goes, the magnetic field lines goes something like this. So any rock that's made that comes out of the earth, the magma that comes out of the earth as lava and then solidifies, while it's still in liquid form, while that lava or magma is still in a liquid form, all the iron particles, all the little iron particles that are part of the rock, the liquid rock, are still liquids. So they can move around, or fluid. So they can all line up, and they line up in orientation with the magnetic field lines of the Earth. So if this rock were made on the Earth while north was north and south was south, so the magnetic field lines flowed in this direction, then this rock would have a north. If you dug that rock up or put it over that magnetic field device, put it over the rock, you get a north and a south that matches the magnetic field lines of the Earth. That made sense to everybody. Now, what could make these magnetic field lines be exactly the opposite? What could make the magnetic field lines flip? Well, it had to happen while the rock was being made. It had to be for north to go south and south to go north. The magnetic field of the Earth must have flipped, and the rock must have been fluid when it was flipped. So the rock must have been made when the magnetic field lines of the Earth were in reverse. And indeed, we know today that the Earth's magnetic field is flipping. The north is going south and south is going north. And we know at some point in the near future, the North Pole will become the South Pole, and the South Pole the North Pole. Now, that doesn't mean that the land is going to flip, but the magnetic fields, right, the force field that is driven by iron in the Earth swirling, these magnetic fields are going to switch. Why do they switch? I'm not sure anybody knows. We know they happen periodically. We know that they happen almost in a fairly regular fashion. And we know that any rocks made during that particular period, for instance, if any rock is made today, it's going to be oriented so that the north is pointing north and the south is pointing south, because all the iron particles in the rock are going to align themselves according to this magnetic field that exists today, which is north and south is south. But any rock made after the magnetic field flips, where south is north and north is south, then those rocks are their magnetic field is going to be flipped. So what we have here is evidence then, when put together with what Alfred Wagner had discovered in the 30s, 30 years before, this naval captain went back and forth across the ocean, was the geomagnetic field lines were switching, that on each side of the this line there were these consistent north-south flips from the center line. The fossils were the same in Africa as they were in South America and Antarctica. The rock layers matched. North America matched with Europe. The Australia, India, and Africa matched in a lot of their fossils. A lot of their orientations, India and Australia, for instance, matched very much in their orientation. When they looked at the magnetic layers of the deeper rocks, they saw that in South America, north was north, south was south. In Antarctica, though, in the same layer, the same area of rock, this is continental now. This is not oceanic. This is oceanic crust. So something weird was happening here. We were switching. Here, though, in South America, north was north, south was south. In Africa, north was just slightly to the left. These rocks had an orientation that was slightly to the left. In India, the magnetic field of the rock actually pointed in this direction. A good, 30 degrees, 33 degrees to the west versus straight up and down north. Australia also 30 degrees to the west. Here in Antarctica is about 20 degrees to the right. So why would the magnetic field, the geomagnetic poles of these particular rocks 150 million years ago, why would they look at how they're oriented? Even though the rock layers are all the same, they're oriented in an odd way. So these, ideally, theoretically, all these were made at the same time. We have radioactive dating that would tell us that they were all made at the same time. So it wasn't that they were molten. It wasn't that they were liquid when the magnetic field lines switched, and even if they had switched north to south, they would not have switched in these odd angles. Well, if you can imagine if, let's just take a look at Antarctica, right? Let's take a close-up look at Antarctica. Imagine if Wagner was correct, the land, Antarctica, was pointing north when that rock was made, that land was pointing north in this direction. South America was pointing pretty much in the direction it is now. Africa used to be pointing in this direction, but now it's pointing in this direction. So it was like this. Antarctica was like this, separately moving around horizontally on an axis. India, at some point, was like this, right? Because that would be north. But somehow, over time, it actually twisted this way. And Australia was like this, but somehow over time, it moved in that orientation. So that was suggesting that those magnetic lines suggest how they moved horizontally, that they actually turned in Australia would have turned in a counterclockwise, in India also in counterclockwise fashion, Africa slightly counterclockwise, Antarctica actually turned clockwise, while South America turned only slightly. So then not only do these lines suggest separation, right? Because this suggested that these were all liquid at the same time, and then these were liquid at a different time, and these were liquid at a different time. But it also suggested that these here were turning in circles. The fossils that are the same on each side suggest that these land masses were connected. Now, if it was just one group of fossils or a couple groups of fossils, or if the fossils here were the same as the fossils over here, one might think that maybe they crossed the ocean, like we discussed when we talked about island colonization. But it's not just that they matched perfectly with the geology and the geography of the land masses. Everything seemed to be pointing that Alfred Wagner's theories were correct. The magnetic field lines flipping, the land pieces fitting, the rock strata, the types of rocks matching, the magnetic fields on the continents themselves aligning in such a way that when you cut them out and turn them, all the compasses would point to this in the same direction. And when you look at how the glaciers moved 350 to 230 million years ago, and how the direction of movement of those glaciers, when you put these land pieces back together again, those glacier movements make sense, as they follow the same path as if all these land masses were together and the glaciers moved across the land while it was still together. All right. There's a lot of good evidence there, but still they were missing that one piece, the mechanism by which this land could be moved. And today we know, and we've discussed it, these ideas of convection currents in the Earth's surface. And we know this because of seismographs, the ability to, when earthquakes happen, we're able to tell how quickly the Earth, the sound, the shaking, the vibrations of the Earth move through the Earth, because of the different speeds that they move through liquid versus solid. We're able to tell that the Earth's inside, underneath the Earth's surface, the layers of the Earth are not all solid, that there are liquid layers and semi-liquid layers, and let's not say liquid, let's say fluid layers and semi-fluid layers and solid layers. And these layerings suggest that because of heat rises and colder material sinks, due to density differences, we get those convection currents that we discussed earlier. And those convection currents allow these plates to move. Later on with radar, we were able to see that the bottom of the ocean is not flat, that there are mountains and ridges. In fact, this center line is composed of a mid-Atlantic ridge where the earth is open, split open with volcanoes spewing forth new land all the time, as along this boundary, it's called a divergent boundary. Along this boundary, what we have is movement in opposite directions. Divergent, meaning moving away from. All right, moving away from this center line. So there's a convection current underneath this land that's moving in this direction, like so. As the magma rises and sinks, this current turns in this direction, this in this direction, pushing the land here that's newly made out towards the continents, and this land out towards these continents. Then when it gets here to North America, South America, Africa, Europe, you have what's called a subduction zone, because the continental shelves are less dense. They float on top. The oceanic plates are more dense. They sink. So this is all new land compared to the continental land, the land on the continents, on the land itself, versus the continent, the plates that are underneath the oceans. The lands, the material, the soil, the rock on land is much older than the rock that's at the bottom of the ocean, since that land that's at the bottom of the ocean actually sinks. Those plates sink and get melted again in the rock cycle. And that explains how these lines can keep reforming and keep flipping, and why the continental plates have stayed fairly consistent over time, because they haven't been melted. So here you have these land masses, these directions of the ice sheets are listed here, geomagnetic pole directions listed here, distribution of fossils. You'll see there's a fossil here, and these fossils are the same here and here. They're all the same. Notice the rock layer here, here, and here is the same. Notice the rock layer here is the same as the rock layer here. Also, if you think about it, if you have to twist this to the left, you have to twist this to the right to get both these compasses to point north. This layer then matches this layer. Isn't that interesting? If you just take it and twist it, this layer would meet this layer. Now, this is a completely different set of data, different set of evidence. But if you made the compass directions match, you would see that the layers of rock also matched. And also, by the way, if you did that, if you twisted this left and this right, not only would the rock layers match, the magnetic field lines would match, but so would the direction of the ice sheet movement. Notice this would then point north, and this would point a little more north too, so they would actually move in the same direction. Interesting. When you twist, you see this layer matches here, you see this layer matches there. If you turn this in this direction, you start to see that those rock layers, if you put this here, this part of this rock layer, this old Precambrian, would match this rock layer, and this part of this rock layer would match this rock layer. So the rock layers start to match across the world if you line them all up and you connect them. You'll notice that these are late Paleozoic, and you'll note that this late Paleozoic, these all match. All this land, all these rocks match. Well, if we take a look at what the fossils would look like if we put them together, they would look something like this. So looking, when we put the land masses together, all of a sudden the fossil evidence makes perfect sense. If these land masses were all connected, then these animals could have easily walked across, and this could have been part of their territory, or they could have been cousin groups or different populations of them all across this land because they could just walk over versus being separated by an entire ocean, right? So it seems, with all this evidence, it seems likely that we have something called continental drift, and that continental drift separated these populations, and over time, these two populations, obviously some of them went extinct, but some changed. You get a different set of animals living in South America today than you get in Africa because the conditions have changed and the populations have been isolated for so long. Now you have some directions here to go ahead and use this data, all this information, the next couple pages, follow these directions, right? Come up with a deduction, cut them out, paste them together, follow the direction of the ancient ice sheets, do your best to orient them in such a way to make everything match up. The next few pages, I think you'll see that one of the pages has a blank so that you can cut out these continents, and then you can go ahead and draw some of the arrows or the compasses the way they're oriented here, and then you can go ahead and cut them out and try to paste them together in such a way as to make them match the way you would see here, this example. Well, I hope this helped with your project, and I hope you see that all this evidence, all discovered by a meteorologist, a man studying the weather in the Arctic, who in his balloon looked down and saw how the ice shifted and banged into each other and separated, and then later looking at the map of the world, thought that these things could be floating on some kind of magma ocean, just like the ice was floating on the ocean in the Arctic. And this man's dreams, this man's passion for trying to discover how things work, he died doing it, and his wife actually said leave his body there, since that's where his life has been spent, in order to honor him. This guy is responsible for us understanding why and how these tectonic plates moved. It also helps explain how populations could have been isolated, and help explain why we have so many different species in South America than we do in Africa, than you do in Asia, and then you do in North America, etc. The interrelatedness of the organisms of life in evolution is partly explained by continental drift and the separation of the populations over time. So go ahead and take a look at this, cut it all up, put it together, and hopefully you'll understand what continental drift is. All right, have a good one. Southern Beach. So in the history of the Earth, about 200 million years ago, it was Pangea that had Africa, or South America, connected to Africa by this, in this supercontinent. North America, which Canada would be here, Alaska here. This would be This is the United States. All would be connected to Europe and then Asia. They call it Eurasia here, right? So this would be China and Mongolia, Russia. Here's Korea, the Korean Peninsula, and all the various Japanese islands, etc. Antarctica would be down here, Australia, Antarctica, right? Or Australia and Antarctica. Antarctica is bigger than Australia. Well, that's how it would be broken down. Now, about 120 million years ago, the southern continents broke off, kind of, and formed this giant landmass called Gondwana, and Laurasia was up here, where there again would be North America, including Canada and the United States, and Mexico sitting out here somewhere. And here's Eurasia, where Europe and Asia, including India and China and Russia and the various Korean peninsulas, etc. And then, of course, that would be broken up, and this would move down, twist to the right, and this would move, twist to the left. This would twist to the right, move this way. Africa would twist up to the right and move underneath Asia. South America would move just up and meet up with North America. Antarctica would stay down here in the South Pole. Australia would move up to this region. So the question is this tree, southern beech, which is found in the southern hemisphere, so it's found down here where Gondwana land would be. So this would be Gondwana. And you can find this tree in Australia, including New Zealand. Now, New Zealand is an island, is a large island, right? That's off the coast of Australia. And southern South America, so South America, Australia. It can also, fossils of it have been found in Antarctica. So Antarctica, Australia, South America, southern tip of South America, right? So around this region here. And the seeds are not readily dispersed by wind, so they can't. So southern beech, the seeds, wind doesn't spread them, so they can't fly over by a storm over the ocean. They can't, and they're quickly killed by salt water. If they touch salt water, they can't float to other islands because as they touch the salt water, they're pretty much gonna be killed. So what's interesting is that it can only be found in places like New Caledonia, New Guinea, Eastern Australia, that's this area here, right? Antarctica, southern tip of South America. But none can be found in Africa. So why can't we find any in Africa or India? India would be up here. Maybe this is India here. I'm not sure. Africa and India. So why not? Again, it can be found in Australia. Once Australia moves in another 100 some odd million years, Australia is going to move up here, South America up there. The southern tip of South America, Antarctica and Australia can be found, but not in Africa. Use a colored pen to indicate the distribution of the fungus in the current world map on the previous page and on your completed map of Gondwana above. So if you were going to place this plant, you would probably do it here, right? You'd probably say, well, it's growing here. I'm trying to get some color that sticks out. So it would be here somewhere, just south of Africa, where it was first grew. There would be here, right? And so it would be something like this on the map. Something south of Africa, right? South of the tip of Africa, of the land that would someday become Africa, because it's not Africa yet. 120 million years ago, there was no Africa or South America or Antarctica or Australia. These continents were created by this continental drift shifting and breaking apart and shifting these continents around. When you're considering the answer to these questions, however, you need to consider the map on the previous page and where these rocks, when you look at this land, where these rocks end up. When you look at the south or the western edge of South America, you have a specific type of rock that's a specific age, right? And that same rock, if you follow that rock layer, it's dark black on the previous page. In fact, let me just show it to you here. Here you see this dark black line. That's a rock layer. There it is. This is late Mesozoic, about 160 million years to 70 million years ago. There it is. You'll note that there's none of this black rock in Africa. It's only in the South American tip. Australia, it's in New Zealand, it's in New Caledonia, it's in New Guinea. Gee, isn't that very similar to what they're telling you here, right? New Caledonia, New Guinea, Eastern Australia. Eastern Australia would be here. Including Tasmania, New Zealand, South America, southern South America. Now remember, when these were all together, they were all down here, this area here. So as this is being, so I don't know why I can't get that darker, but as you're looking at South Australia, Antarctica, southern tip, you circle this, that includes all those lands that we just discussed. And at what age would that rock be? About 160 to 70 million years ago. So consider that when you're consider the placement of all this land, these lands that have been identified here when they were all part of one continent. And you can see I highlighted here, but there it is. So now you would see the distribution, the biogeographical distribution of this plant called southern beech could only be found if it developed here, if it spread here, if it lived in forests here, is this southern beech. Then Gondwanaland broke up and all the continents formed. Where would you find those trees after? You'd find their fossils in Antarctica as they died because it got too cold down in the southern pole. You'd find them in the southern tip of South America because that's where they were when the forests were first settled. Australia, you'd find them in Australia, New Caledonia. You'd find in New Guinea because that's where they are. You see, there's New Guinea. This land would move up, and that would become New Guinea, and part of it would become New Zealand, right? And this here would become Australia, as it all moved up and twisted to the left. It was down here, and it moved up and twisted to the left. So you'd expect to find this southern beech in all these areas. You wouldn't expect to find it in Africa because it never, once Africa separated and became its own continent, there was no way for these southern beech trees to get from here in Australia over here to Africa, or from here, southern tip of South America to Africa, or Australia to Africa, because they were geographically isolated. The ocean waters would have stopped the beech from moving. And I think I just pretty much helped you answer all those questions there. All right, so we talked about the seafloor spreading. We talked about the evidence of seafloor spreading. We've done we've done radar imaging, we've done magnetic imaging, and we know that there's plenty of evidence that suggests that this Atlantic Ocean spreading apart. If we know the Atlantic Ocean is currently opening up, in other words, this rift is opening up at 2 centimeters per year, how long would it have taken for South America and Africa to have separated by 23 kilometers? Well, I'm going to set up this problem for you because I fear you're not as well versed in the factor label method as I'd like you to be, but you should be able to figure this out on your own. However, I'll go ahead and walk you through it. If you have 2 centimeters per 1 year, all right, and you need conversion factors because you want to know how long, how much time did it take to separate by 2,300 kilometers. And you need to have, in the end, you need to have how many years. That's what you want to know. Well, if you know that there is 100 centimeters in 1 meter, how do I know that? Because I know my units, and I know that centi means 100, and I know that a meter has 100 centimeters in it. So I know now that centimeters cancel. Now, if I also know that there are 1,000 meters in 1 kilometer, right? And I'm going to actually make an argument that this is kind of wrong because what I want is I want time on top. I want to know the years. So I'm going to go ahead and take the initiative and flip this. 1 year is equal to 2 centimeters. So I'm going to go ahead and flip this. Now, you might ask, well, how can you flip it? Well, let me ask you something. If I have 2 over 2, that equals 1. Does it matter if I put 2 over 2 or rearrange? Isn't it the same if I take 2 and put it over 2? Aren't those two things the same? So if in other words, I have A over A, and I switch them and I put A over A, it's still equal to 1. If I divide them, they're both equal to 1. All right, so they're equal. So if I tell you that 1 year is equal to if I tell you that 1 year is equal to 2 centimeters, that means they're the same. That's like saying 2 equals 2 or A equals A. So I can put 1 year over 2 centimeters, or I can put 2 centimeters over 1 year, and it's the same number because they're equal, right? We call that an equality. So understand that because we say they're equal, that means that we can put either one of them on top and it'd be all right. So I'm going to put year on top. And if I put year on top and I'm trying to get rid of centimeters, I'm going to want to put 100 centimeters on top. How come I can put 100 centimeters on top and 1 meter on the bottom? Because as I said, they're equal. There's 100 centimeters is equal is equal to 1 meter. So I'm allowed to do that, and centimeters cancel out. Why did I put 100 centimeters on top? So I could cancel out centimeters. Now I need to get rid of meters. I need kilometers, because ultimately I'm going to want to get rid of kilometers. How do I know that? I know that from the problem. I know that from the problem. If I look at the problem, it says 2,300 kilometers. So I have to know 2,300 kilometers. I'm trying to get rid of that. I'm trying to find how much time it would take to move that, right? So I need to find the rate in terms of kilometers. So in 1 year, it would have moved 2 centimeters, but I got rid of centimeters. Now I got meters. So if it moved 1 year, it moved 2 centimeters. Then in 1 year, it would have moved. It would have taken, if it takes 1 year to move 2 centimeters. If you think about it, if you just stop right now, 1 year it would take 1 year to move 2 centimeters. If you did the math, it would take 100 years to do 2 meters, right? So already it seems to be working. So I'm testing myself, I'm testing what I'm doing, and it makes sense. Now I need to get rid of meters and put kilometers, and I know that there's 1,000 meters. 1,000 meters in 1 kilometer. So now I can get rid of meters, and I have kilometers. And then lastly, I can get rid of kilometers if I just multiply times 2,300 kilometers over 1, because every number is over 1. We've learned that if you have A is equal to A over 1, right? X is equal to X over 1. We all should know that from algebra. We're fine with that, I think. So what you get, once you cancel kilometers, what's the only unit you have left? It's years. So when you do the math, when you take 1 times 100 would be 100, times 1,000 would be 100,000, times 2,300 that would equal 230 million years. How do I know it's years? Because that's the only unit that's left. It's 230 million years. That's the only unit of measurement left. That's how many years it would have taken for the continents to separate. Now I did the math for you again. I'm not, and the reason is I just didn't feel comfortable thinking that if you did it on your own, that's great. If you didn't, you could check your work. If you didn't do it on your own, well, you just did it with me here, hopefully. 230 million years. And if you really wanted to get fancy, you would have used scientific notation. I just want to show you how much easier scientific notation would have made this. So if we used 1 year in scientific notation, we would say 1.1 times 10 to the 0, because 10 to the 0 is 1. I don't know if you knew that, but any number to the 0 power is equal to 1. A million to the 0 power is equal to 1. 1 times 1 is 1, so this is 1. That might be a little more difficult than just writing the number 1, that's true. But you'll see it'll save you time in the long run. Wait a second, let me unjoin this. So when we then take this 1 times 10 to the 0, and we say, well, we put that over 2 centimeters, so that's 2.0 times 10 to the 0 centimeters. So far it's not easier, I agree. And then you say 1 times 10 to the second power. Now why second? Because what the positive integer positive exponent tells you, you can move the decimal to the right. So if you have, and that's not correctly written, it's a lazy person's writing, 1.0 times 10 to the second power. And you'll notice that when you have 0.0, if you move it twice, 1, 2, you'll end up with 100. That's the same as 100 centimeters. So even though it's the same, the math will be easier if you do it this way. 1 meter, and this is centimeters. Centimeters cancels. Again, you're leaving years, which you want. Then you go ahead and do 1,000, but again, 1,000 would be 1.0 times 10 to the third. Now, again, you move the decimal 3 times, you'll have a number of 1,000 meters. If you learn this, you're likely to be more successful, especially in physics. And again, you're going to cancel out meters. And then 2,300 kilometers would be 2.3 times 10 to the third power. So you move the decimal 3 times to the right, you get 2,300 or 2,300 kilometers over 1. And what number would that get you in the end? Well, let's go ahead and look and see how this does help in the end. It keeps everything neater, simpler. There's less mistakes. Why? Because I know what I'm going to do is add, when I multiply, numbers are in scientific notation. When I multiply numbers with exponents, I add the exponents. When I divide the exponents, I subtract the exponents. And by the way, I made a mistake here again. All these ones should be, let me go ahead and zoom in and write it very small. All these ones should be 1.0 times 10 to the 0 power, 1.0 times 10 to the 0 power, and this should be 1, just to be accurate and to keep everything. All right, there's no units there because that's just over 1. All right. So if we go ahead and do our divisions, remembering that you're going to subtract exponents when you're dividing, you're going to add exponents when you're multiplying. Well, what's 1 times, let's just the integers, these numbers in front of the x, in front of the multiplication sign, you're going to go ahead and multiply. So 1 times 1 times 1 is 1, times 2.3 is 2.3. 2.3, that's easy. And And by the way, I got this. No, this initial one was wrong. It was 23 million years divided by 2. I just saw that. 2.3. But then I have to multiply the exponents. I have to multiply these 10 to the second, 10 to the third, 10 to the third. So what do? I add the exponents. So that's 3 plus 3 is 6 plus 2 is 8, right? So it's 2.3 times 10 to the 8th power. And that's divided by 2.0. And I'm adding the exponents here. 0 plus 0 plus 0 plus 0 is 0. And I'm going to multiply the coefficients. 2 times 1 times 1 times 1 is 2. So it's 2.0 times 10 to the 0 power. So if I divide 2.3 by 2.0, I get 1.15. And if I really want to get into significant digits, I would go ahead and keep the second 0 all the way across. So you need at least one decimal on the one decimal place after the decimal, but you can add as many significant digits as you'd like. We can discuss that later if you like. 1.15, that's the division of these integers. And then what do I do when I have two numbers that have exponents? I subtract the exponents as long as they have the same base number, and 10, it's 10 here and it's 10 here, so they're the same, times 10, 8 minus 0, which would be 8. So it's 1.15 times 10 to the 8th years. Now the question is, well, what does that mean in numbers? Does it equal the same as 230 million years divided by 2? Well, 230 million years divided by 2 would equal 150 million years. Now, how many decimal places do you see in 150 million years? Well, if I moved it from here, this is where the decimal is now. If I moved it all the way to the one digit, where there's only one digit to the left of the decimal, if I did that, it would be 1, 2, 3, 4, 5. So let me redo that. 1, 2, 3, 4, 5, 6, 7, 8. So 8 would be 1.5 times 10 to the 8th would equal 150 million years. So if I took then, let me do the opposite. Let me take 1.15 and go ahead and multiply times 10 to the 8th by moving the decimal 8 times. 1, 2, 3, I'm going to put a 0. 4, I'm going to put a 0. 5, I'm going to put a 0. 6, I'm going to put a 0. 7, I'm going to put a 0. And 8, I'm going to put a 0. Years. That's what this means, right? Times 10 to the 8th would mean move the decimal 8 times to the right. And I went ahead and put in the commas. 3, there'd be a comma here. 3, there'd be a comma here. So that's 115 million years. And so the numbers are equal. Now, why is this easier? It's easier because I don't have as many zeros and less likely for me to make a mistake. In fact, I caught a mistake I made simply because I was looking at it with less confounding information. I can easily multiply 1 times 1 times 1 times 2.3. It's a little harder in my mind to multiply 1 times 100 times 1,000 times 2,300. And it's easier for me to add the exponents 0, 2, 3, 3 to get 8, 0, 0, 0, 0 to get 0, 2 times 1 times 1 times 1 to get 2. It's easier for me to take 2.3 and divide by 2 rather than take 23 million divided by 2. Not that this is much more difficult, but it can be very it can lead you to make errors with all these zeros. I could have easily put 15 million or 150,000 instead of 150 million just because I have all those zeros. Keeping it neat with the exponents makes it a lot easier, and then allows you to double check and lets you look and see, is this number reasonable? Is a factor of 8 reasonable? I can go back and look and see quickly that 3 plus 3 plus 2 is 8. All right. So scientific notation does help a lot. Hopefully you get used to using the scientific notation and that you get used to using significant digits in the long run. It makes your life easier, and you'll have to do it as you go along in the sciences and in the medical field if you decide to go in the medical field. All right. So when you're thinking about how continental drifts help support evolutionary theory, remember the distribution of species, the biodistribution, right? The biogeography of life on Earth. The biogeography of life on Earth makes it quite difficult to understand why you would get fossils here that would not, and here that are not found anywhere else. Why do you find fossils here, here, and here, and these fossils aren't found here or over here or over here? And continental drift helps explain that, because it would make sense if all these were originated, were all oriented in one giant massive landmass, in the late Mesozoic, let's say, or in the late Paleozoic, because this looks like when Listosaurus was distributed. If it was 240 million years ago, then it was. If that's the most recent fossil we can find. It's 230 million years ago of this particular dinosaur, and then it went extinct. We don't see it anymore in the fossil record, and therefore we would expect that it was around during Pangea, when all the land masses were together. This idea of Pangea could only have come into play if we understood that these continents do drift apart. They are separating. In fact, we can measure it at 2 centimeters per year right now. The Atlantic Ocean is spreading at 2 centimeters per year. It's something we can actually measure. That's a fact. That's not a theory. The theory explains how, right? The theory explains how that fact happens. How does the seafloor spread? Well, we know it's spreading at 2 centimeters per year, but it's explained by this idea of continental drift and convection currents and the plates separating. So in any case, the explanation, the continental drift concept really does help to understand, right? It really does help to understand evolution, because it helps explain the distribution of fossils around the world. And in fact, a lot of these fossils end up lining up. A lot of these fossil finds line up with the concept that Pangea existed. Again, if we're making an if-then statement the way we keep saying, and we say to ourselves, well, if evolution is true and organisms, we are descended from our parents and our parents descended from their parents, and we have these species that occur on 3 different continents. How did they get there? Why only here? Why are they not found all over the place? And if it were true, that would mean that these three dinosaurs must have either been able to swim, which they could not, there must not have been ocean between them, or they must have been able to swim. Well, because of Pangea, we know that the answer that supports it is that the land masses were all at one. There was no ocean between them. So evolution would have predicted one of those two things, and in fact, one of those two things did it. We, based on magnetic evidence and geological evidence and fossil evidence, we see that this is correct, that Pangea was probably in existence, that we did have a supercontinent at one point, and the fact that the two continents are still separating to this day and we can measure it. All that together supports the idea that Pangea was a thing. And if Pangea was a thing, then that would explain why the distribution of these fossils. All right. So they support each other. The ideas support each other. One would predict the other, and in fact, both are true. So, all right. That's it for Continental Drift and evolution in Gondwana land. And this is the cutout you're supposed to cut out and orient in such a way as to explain both the magnetic and you've seen the Gondwana land and the Pangea maps. You have time. I would cut them out and play around with them. I would try to put them together like puzzle pieces rather than just looking at the answer and trying to work backwards. You can do that too, but you're hurting yourself. You're not giving yourself the opportunity to figure this out on your own. Use the answers that you have in the previous part of this video where you see how they fit together, and instead use them to check your answers rather than to guide your answers. So look at the evidence, look at the magnetic evidence, look at the orientation of the ice flows, look at the rock layering, and position these, move backwards and position these the way they would have been had they formed one continent. How would these have fit together? This is left blank, and it's in fact the other side was printed on so that you could cut them out.